Okay, back to exponential, but this time we're going to model with exponential functions. I'm going to show you some real-life applications and some equations that you don't have to worry about memorizing. You just kind of have to know which one goes with which. Okay, again, with exponential functions, it's all about base. If your base is bigger than 1, it's going to grow and it's going to increase really quickly. Hence, something grows exponentially. If you've ever heard that phrase, it grows really fast. If that base is between 0 and 1, again, it can't be negative. It's all about basically a fraction smaller than 1 but bigger than 0. It's going to decrease really quickly. So here's the general growth formula for exponential growth. You got A as your initial amount, 1 and plus are part of the formula. R is going to be your rate. Okay, now that rate is usually as a percent, and you want to make sure you take that percent and you convert it into a decimal. And then T, or your exponent there, T is your time in this case. So let's say we got the population of growth in West Fargo. It's growing exponentially at a rate of 5%. Okay, so that's going to be my R equals 5%, but use 0.05. Okay, we have an initial amount. So in the year 2019, the population was 1,000. With the population, Fargo being in 2022. So what we're going to do is time is going to be 2022 to 2018. So in this case, it's going to be 4 years. Okay, so Y is our final population in 2022. So Y equals 35,000. 1 plus 0.05 raised to the 4th power. Okay, what I'm going to do is I'm going to do my order of operations. I'm going to add that first in parentheses. And notice how this is a number bigger than 1, so it's going to be growth, albeit not that big. Okay, so I'll take 1.05 to the 4th power. And yeah, you're going to get a calculator for this. And then I'm going to leave all those decimals in my calculator. I'm just going to hit times 35,000. And that leaves me with 42,542.7 or 42,543 people in West Fargo in the year 2022. Okay, so that's the general growth. There are certain growth formulas that are for certain things. For example, this one's a growth formula as well because it's got a plus in there, and I'm going to get a number that's bigger than 1 as my base. It's 1 for compounding interest. So P is the principal. That's the initial part. And I'm going to go down to my description. It says your deposit $500. That's going to be my principal. Okay, your rate, it's going to pay 3% annually. So 3%, again, convert that into a decimal, 0.03. Okay, now N is the number of time it compounds yearly. So in my example here, I'm going to go with annual. So N equals 1. Quarterly would mean that N is equal to 4. Monthly would be N is equal to 12. If you wanted to go like D, daily, that is going to be N is equal to 364. Okay, that's how many times you get interest in a year. In this case, it's going to change. So T is time, and it's going to be over those 2 years. So to find the amount that's in my account, I'm going to take my principal of $500. 1 plus 0.03 divided by 1, and it's 1 times 2. Now that 1 is the N, T is that 2. So I'm going to do what's in parentheses first. So 1 plus 0.03, raise that to the 2nd power, okay, times 500. And the interest compounding annually, so once a year for 2 years is, or not interest, but the amount that's in there is $530.45. So essentially I made $30.45. Okay, quarterly, save 500. But now I'm going to have 1 plus, and that rate is going to be divided over those 4 instances. So that's why that R is divided by 4. And then it's going to be 4 times 2, which is going to turn into 8. So now instead of my parentheses, I like to take the 0.03, divide that by 4 first, then add 1. Okay, and then I'm going to raise that to the 8th power, and then I'm going to multiply that by 500. And now that gives me $530.799. So we're going to round that up to $530.80. Okay, a little bit more than it was for annually, which is good because my interest compounded a little bit better. Now, when it comes to monthly, again, same thing, 500. But now, left the issues. Now it's 1 plus 1 point, or my rate divided by 12. And now it's going to be 12 times 2. So I'm going to raise that to the 24th power. So again, 0.03 divided by 12. Okay, I'm going to add 1 to that. And then we'll raise that to the 24th power times 500. Okay, and I got 530 again. 0.878, so we'll round that to 88. So 8 cents bigger, but again, it's 8 cents just by compounding that monthly. Okay, and for daily, and it would be 625. So that's compounding interest. Again, it's growth. If I actually keep this as continuously compounding, that's when I'm going to use this letter E. And it's on your calculator. You can type it in and hit enter, and you should get like 2.718 and a bunch of other stuff. It's irrational. Keeps on going forever. A is still the final amount. P is still my principal. My rate is still going to be that rate percentage in decimal form. And then T is the time in years. Except for now this E is this number that's 2.718. So I got a bank account that computes interest continuously. And that's like the ding, 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 ding continuously tells me to use this formula. Okay, I got my rate of, 0.025. I'm leaving the $5,000 in there for, I believe it's 5 years. So A equals 5,000 E to the 120.25 times 5. Okay, so on my graphing calculator, that E is just above the ln, so I'll hit second ln. And I'm going to go 0.025 times 5. Okay, that's 1.5,000 times 1.133. And again, I'm going to keep all my decimals, so on my calculator I'll hit times 5,000. And that's going to give me an amount of 5,665.74. In fact, if you're searching for a bank account, you're going to want to grab a bank account that compounds continuously. It's your best bet, best rate, or not necessarily your best rate, but your best compounding. All right, so then the last one is exponential decay, things that shrink. And what's going to change is that growth formula was a plus, now it's going to be a minus. This happens a lot in half-life if you take chemistry. Okay, half-life is just things decreasing by a factor of 1/2. So it would be like a 1/2 to the x power or 1/2 to the t power. Okay, so I've got this radioactive decay. Y is the grams of the sample, iodine 131. That's just the name of the iodine. T is the number of years, and here's the model. It's 50 parentheses 0.92 T. Now, I know this is decay because the base is smaller than 1. Well, I want to find the initial amount. Well, that initial amount is just that number before I do anything really with it, the 50. Or you can think about it as like that time being 0 years. And what's going to happen with that base, if I raise it to the 0 power, is that's going to turn into 1, and that leaves you with 50. So in other words, there's 50 grams to start off with. Okay, what percent is it decaying per year? Well, I'm going to take this base, and I'm going to compare it to that right there. I'm really solving this. And really, I went down by 8% or 0.08. Okay, so 8% would be the rate of decay. Okay, and some applications. I mean, you could figure out maybe what, option C, how many grams after, say, 5 days. And what that would look like is you would take 50.92 and you're going to raise that to the 5th power. And you would get something like here. I'll calculate it out. 0.92 raised to the 5th power times 50. You would be left with 32.95 grams. Something smaller than your initial 50. Okay, so here we go. Kind of the idea here with ibuprofen. So an adult takes 400 milligrams. So there's your A, your initial amount. Y is the number of hours. X is the amount of ibuprofen in a person's system that decreases by 29%. So 1 minus the 0.29. Very important that you make sure that you change that to a decimal. So that's going to be 0.71. And it can be T, it can be really X if you wanted to. It doesn't really matter for your exponent. But how much ibuprofen or milligrams of ibuprofen is in the system after 3 hours? That just means that I'm going to put in this 0.71 to the third power and multiply that by 400. Okay, so that 400 got knocked down to, after 3 hours, 143.16 milligrams. And that is modeling exponential growth and exponential decay.